Let's say you wanted to find the value of the function x plus y whole squared minus 1 over x plus y minus 1 at the point 0, comma 1. So that is x equals 0 and y equals 1. If you plug that in, you would get 1 squared minus 1 over 1 minus 1, and that's just 0 over 0. And 0 over 0 along with some other forms is called an indeterminate. Now the other forms that are regarded as indeterminates are infinity over infinity, 0 times infinity, and 1 to the power infinity. If you get any of these expressions, when you plug in something, you really can't analyze the function because you really don't have an idea of how the function behaves just by plugging in the value. This is where limits come in. So we use limits to analyze these types of functions and to analyze functions in general. So to know how this function would have behaved, this multivariable function would have behaved, we would have written limit as x and y approach the point 0, comma 1, and we would solve for it. So you can't put it, we know that if you put it, you get an indeterminate form. What you can do is you can factorize this numerator into, since 1 is just 1 squared, you can factorize this into x plus y minus 1 times x plus y plus 1. A plus b, a minus b equals a squared minus b squared, and since that is just divided by x plus y minus 1, you can just cancel these terms out. So what you're left with in the end is limit as xy approach 0, comma 1 of x plus y plus 1, and that, if you put it in, is just equal to 2. Now the limit of multivariable functions can be defined formally. It can be defined formally, but let's look at the informal part first. So let's say you had a function, you had a really random function, and in this random function, let's say it had a structure of a sheet. Let's say it looked something like this. And in this function, I look at a certain point, and I say that that point is the output of putting x naught, y naught into the function f of xy. So this can be the x-axis, this can be the y-axis, this can be the z-axis. And when you do that, and let's say that for plugging in x naught, y naught, the function's not defined, just like in the case that we had here, it's not defined. So instead what you do is you start putting values that are really close to this value. So let's say somewhere here you take some point here that's really close to x naught, y naught, and you find what's the value is, and then you come increasingly close to it, the point x naught, y naught, and ultimately observe that it limits the values that you find limits to a certain value. In this case it would be 2. So the area of approach, the way you are approaching to find the limit can be defined in several ways. So either you can approach through, either x and y can approach through a certain path. So let's say that there are certain lines on the xy plane through which you approach and check whether the limit is 2 or whatever number you have. A more general approach would be to check for these values of the function f of xy for x's and y's lying in some unit circle centered along x naught, y naught. So if you look in the xy axis, xy coordinate plane, let's say that x naught y naught was here, x naught y naught, and at this point right here the function's not defined, so undefined, and around it in some neighborhood it is defined. So let's say you take a neighborhood of x naught y naught with radius delta. So for all points, if for all points lying within this disk, you get increasingly close to the value of 2 in this as the limit of this function, you can say that the limit of this function f of xy is actually equal to 2. Now to write this more formally, we can say that the limit as xy approach x naught y naught of f of xy equals a certain number L if for every number epsilon greater than 0 there exists a corresponding number delta greater than 0 which for all xy's in the domain of f satisfy something like this. So they satisfy this property. So the distance from x naught y naught, that's just this formula right here, is less than delta for every epsilon that you give me. So that just means that I can take a really, let's understand what the definition means. I can take a really small number epsilon right here. I can plug that in and I can get to really close to the limit L, still not equal to though, and I can always find x's and y's lying in some neighborhood of the actual point that we are considering. And in this case we are saying that it's a disk. So what that means is essentially we are saying that we can get really close to this limit by changing the x and y's that we have. Now this formal definition comes to some use, but when you're actually evaluating limits, it comes to really little use. So what you can do is you can extend your perception of evaluation of limits from one variable to two variable. That's what we did right now with the first example, and now we can extend it to even more than two variables. Let's try 4 variables. So let's say you had a function natural log of x squared plus y squared plus z squared plus w squared, and you wanted to calculate the limit as x, y, z, and w approach 0, 0, 0, 1. So if you plug that in, if you plug this number right here, you would arrive at natural log of 0 plus 0 plus 0 plus 1, and since the log of 1 is just 0, you get that the limit of this function is equal to 0 as well. So what that essentially means is that if you were able to plot this function in 5 dimensions, because you will need 4 dimensions for representing the independent variables x, y, z, and w, and 1 variable for representing the output. If you had a 5D 5D representation somewhere, you can check that as you approach this point, this tuple, as you would say, this tuple, this point in the 4-dimension part, you approach 0 on the fifth dimension, that is the dimension of the output. We can even extend this. We can take an infinite number of variables we want to. So the general guide, the general tactic, at least we can say, would be that if you have like any function of 2 variables, and really for just by extending it to more variables doesn't change the perception. If you get it for 2 variables, the same concept applies for more than 2 variables as well. So if you have a function like this, wherein you want to find the limit as y approaches x0 y0, you check that whether f of x0 y0 is defined. If it is defined, it's a number, it's not an indeterminate, then the limit is just equal to that value. Problems arise when this is not defined. So if it's not defined, then you need to reduce it. Reduce it or do something with it. Do any manipulation to get it into a form that's not indeterminate. That's a well-defined number. So in the first example that we did, what we really did is this number, when we plugged it into this function, the function became undefined. So we reduced it, we did some manipulations on that until we didn't get an indeterminate, until we didn't get rid of the indeterminate form. So that's the general introduction to limits. I'll meet you in the next video and we will continue talking about limits of some more interesting functions. I'll see you in the next one.